So you step off a curb, you twist your ankle, and within seconds, right, it swells up.
Oh, yeah.
Instantly. Right. And to you, it probably just feels like a simple, painful inconvenience. Maybe you grab some ice, elevate it, wait for it to pass.
Which is the normal reaction, sure.
Yeah, but if we actually pull back the curtain on the incredible medical text we're getting into today, we see something entirely different.
Oh, completely different.
Yeah, it's this massive, highly technical exploration of systemic trauma and the body's metabolic response.
Yeah.
And what it shows is that your body didn't just like swell up, it literally just declared a microscopic world war.
It's a full-scale mobilization. I mean, your body does not view that twisted ankle as just an inconvenience. It views it as a critical breach in the perimeter.
A literal invasion.
Exactly. We're talking about a highly conserved, millions of years old survival program. It's this staggering symphony of chemical alarms, genetic switches, and cellular infantry that just deploys instantly.
And that is exactly our mission for this deep dive. We're taking this dense clinical textbook, which, by the way, was curated just for you, and translating it into what it really is.
Which is a thriller.
Yes, an epic thriller happening right inside your own veins. We're going to explore this ultimate war room protocol that activates the second you experience an injury.
So much happens so fast.
It really does. So let's unpack this, because the very first thing that happens, the initial alarm sounding in the blood, it completely threw me for a loop.
Serotonin.
Yes. We typically associate physical trauma with, pain signals, but the sources point to serotonin as one of the very first chemicals flooding the zone. And I kind of have to push back here.
Go for it.
Isn't serotonin the famous happy chemical in the brain?
Mm-hmm.
Like, what is a mood regulator doing on the front lines of a physical injury?
Yeah, it's a massive misconception, honestly. Yes, serotonin or 5-hydroxytryptamine, if we're being formal. It's famous for its role in the central nervous system, regulating mood and sleep and all that. But the vast majority of your body's serotonin is actually synthesized far, far away from your brain.
Really? Where?
It's manufactured in your gut by these specialized intestinal cells. And from there, it gets absorbed into your bloodstream and stored in massive, highly concentrated vaults inside your blood platelets.
Wait, platelets like the sticky fragments that clump together to form scabs and stop us from bleeding?
Those are the ones. When you're injured, platelets are the ultimate first responders.
Yeah.
But they're not just paramedics stopping the bleeding with a physical patch.
Okay, so what else are they doing?
They're aggressively handing out chemical weapons. Upon injury, platelets rupture and just dump that stored serotonin directly into the surrounding tissue.
Oh.
Yeah, and in the periphery of your body, serotonin acts as a severe vasoconstrictor. It literally clamps down the local blood vessels to limit bleeding.
Okay, that makes sense.
But simultaneously, it acts as a chemical beacon. It's basically screaming into the void to recruit heavy immune cells, specifically neutrophils, to the site of the damage.
So the platelets are basically dropping a chemical pin on the map to call in the cavalry.
Exactly. And researchers actually proved just how vital this is by looking at genetically modified mice.
Right, I read about this in the text.
Yeah, so they engineered these mice to lack a very specific enzyme called TFH1. You can think of TFH1 as like the main manufacturing plant for peripheral serotonin.
Okay.
Without it, these mice couldn't make any serotonin outside of their brains. And when researchers introduced an inflammatory injury to these mice, the immune response was catastrophic.
It didn't respond.
Well, dramatically fewer neutrophils rolled onto the scene. The cellular troops were essentially wandering lost in the bloodstream because they didn't have that serotonin signal to guide them.
That completely changes how I will ever look at a simple blood clot. And serotonin is just one part of the alarm, right? Histamine is surging at the exact same time. Now, we usually think of histamine as that annoying chemical that makes our eyes water and noses run during allergy season.
Oh, for sure. The allergy chemical.
Yeah, but in a trauma scenario, it's acting more like the battlefield commander.
Absolutely. Histamine is a master regulator because it holds different keys for different cellular locks. When it's released by mast cells and platelets at the injury site, it binds to various receptors to execute entirely different orders.
Okay, break that down for me.
Sure. So when it turns the lock on an H1 receptor, it triggers vasodilation. It forces the nearby blood vessels to expand so the cellular troops have enough physical space to enter the tissue.
Oh, it opens the roads.
Yep. But when it binds to H3 or H4 receptors on the immune cells themselves, it actively modulates their aggression. It dictates how aggressively those cells are going to hunt and how many inflammatory signals they'll produce.
So the chemical alarms are blaring. Serotonin has clamped the bleeding vessels, and histamine has opened the supply routes. But a chemical floating in the blood is just a message. How does that message physically change the behavior of a white blood cell? Like the signal has to somehow cross the cell membrane and reach the DNA, right?
Yeah, and this is where we enter the cellular command center. The sheer scale of the genetic rewrite that happens next is almost unbelievable.
The sources highlight a statistic that honestly made me read it twice.
The 80% one.
Yes, within just 4 to 12 hours of blunt force trauma, more than 80% of your circulating white blood cells' transcriptome shifts.
It's massive.
Their entire genetic programming, over 80% of it, is practically rewritten in a single afternoon.
It's a total reprogramming of the cellular machinery. And the physical mechanism driving this, the way the alarm actually gets from the outside of the cell all the way into the locked vault of the nucleus, relies primarily on what biologists call the JAK-STAT signaling pathway.
The JAK-STAT pathway.
Yeah. It serves as the central communication hub for the entire immune system.
Okay, I love a good mechanism. Walk us through how this JAK-STAT relay race actually functions on a physical level.
All right, picture an inflammatory messenger protein known as a cytokine floating through the blood. It bumps into the outside of a white blood cell and docks into a specific receptor on the cell's surface.
Like a key in a lock.
Exactly. Now, attached to the inside of that receptor, dangling inside the cell, are these dormant enzymes called Janus kinases, or JAKes.
Right.
When the cytokine docks on the outside, it physically forces two receptors to snap together. This pairing jolts the JAKes awake.
So they're activated by that physical snap.
Precisely. The awakened JAKes then grab these passing molecules called STATs, which stands for signal transducers and activators of transcription.
Got it.
The JAKs attach a highly energized phosphate group onto these STATs. The energized STATs then pair up, literally detach from the receptor, and travel deep into the cell, penetrating the nucleus.
They go right into the vault?
Yep. Once inside, they act as master keys, binding directly to the DNA to rip open specific genes and start producing combat proteins.
Wow. It's literally like a courier arriving at the front door with a top-secret launch code, sprinting down the hallway, and plugging it straight into the mainframe.
That is a perfect analogy.
But wait, if 80% of the genes are shifting into combat mode, and these STAT couriers are constantly triggering inflammation, how does the cell keep from just burning itself out?
Well, the body has a built-in self-extinguishing emergency brake.
Oh, really?
Yeah. The very same genetic pathway that triggers the massive inflammation also forces the cell to produce proteins called SOCS suppressors of cytokine signaling.
SOCS, okay.
These SOCS proteins act like internal assassins. They hunt down the activated receptors and physically dismantle them. The system regulates itself by destroying its own signal before the inflammation spirals out of control.
But that raises a really dark question for me.
What's that?
If this system is so perfectly coordinated, if it's been refined over millions of years of evolution to include its own emergency brakes, why do patients with severe trauma sometimes not survive the aftermath? Like, you always hear about people surviving the initial terrible car crash only to pass away in the ICU a week later. Is there some sort of mysterious second hit that sneaks up on them?
That's a really common assumption in medicine, actually, but the sources we're analyzing explicitly correct that misconception.
Oh, they do?
Yeah. Mortality in severe trauma cases isn't usually caused by a unique, mysterious second hit. It's actually caused by the sheer degree and duration of a dysregulated response.
So the brakes fail.
The command center's emergency brakes fail completely. And to understand why, we have to look at epigenetics, which is the physical structure of how your DNA is stored.
Epigenetics meaning like the way the DNA is folded up rather than the genetic code itself.
Exactly. Think of your DNA like an impossibly long thread. To fit inside the nucleus, that thread has to be tightly spooled around protein bobbins called histones.
Okay, bobbins. I can picture that.
If a gene is tightly spooled, the cell can't read it. If it unspools, the gene activates. Well, after a massive trauma, like hemorrhagic shock, the enzymes that control this spooling and unspooling get completely jammed.
They get stuck.
Yeah, the DNA access gets stuck in the open position for inflammatory genes.
So it's not that the DNA is broken. It's that the physical spools are jammed, locking the cell in a state of perpetual emergency.
Spot on. And modern medicine is desperately trying to unjam those spools. The text mentions these fascinating ongoing clinical trials using a drug called valproic acid.
Valproic acid, right.
It operates as an HDAC inhibitor, And without getting bogged down in the complex chemistry, it essentially stops the enzymes from permanently locking the spools.
So doctors are literally trying to drug the epigenetic machinery to manually reboot the patient's cellular command center.
That's exactly what they're doing. They're hacking the bobbins to stop the inflammation.
That is wild. Okay, so the alarms have sounded, the genes are completely reprogrammed. Now the physical troops finally deploy into the tissue. The cellular infantry, here they come.
And based on our sources, the very first wave to hit the beach is always the neutrophils.
Yeah, neutrophils are the grunts of the immune system. They're fast, highly aggressive, and extremely expendable.
And their tactics are unbelievable. The sources describe this defense mechanism they use called nets neutrophil extracellular traps. Oh, nets are fascinating.
The only way I can visualize this is like Spider-Man shooting webs. Like when neutrophils get highly activated by danger signals, they literally rupture themselves to extrude a massive meshwork of their own DNA and chromatin into the surrounding tissue.
That's literally what they do.
They throw a physical, sticky net, heavily laced with toxic enzymes, to trap and kill invading bacteria.
It's a brilliant, vicious mechanism for isolating a bacterial infection. But, and this is a big but, this behavior introduces a profound vulnerability.
How so?
Think about the nature of severe trauma. What happens if there are no bacteria?
Oh.
What if you were in a massive car accident, a blunt force, sterile tissue injury with no open wound or massive infection?
Well, the alarm bells ring just as loudly, so the neutrophils still show up.
Right. And they still throw those toxic DNA nets into your sterile, injured tissue. But because there are no bacteria to trap, those nets just sit there.
Yikes.
Yeah. Your own immune system eventually sweeps the area, sees this exposed, mangled DNA covered in toxic enzymes, and assumes the body is under a massive foreign attack.
Oh, I know.
It registers these nets as autoantigens. This triggers massive friendly fire where your immune system begins attacking your own healthy tissue, causing severe secondary damage.
Wow. A devastating case of the cure being worse than the disease.
Exactly.
And it isn't just the frontline neutrophils causing havoc either. The deep dive goes extensively into the heavy infantry that arrives next to the macrophage.
Key cleanup crew.
Right. And it highlights a critical behavioral shift that practically dictates whether a patient lives or dies. The text calls it the M1 to M2 shift. How does this switch actually dictate recovery?
Well, macrophages are incredibly adaptable. When they first enter the trauma zone, they adopt what's called an M1 phenotype. This is your classical pro-inflammatory attack mode.
So they're on the offensive.
Very much so. They secrete aggressive chemicals like tumor necrosis factor and reactive oxygen species to obliterate anything dead or dangerous. But a tissue cannot heal while it's being actively bombed.
Makes sense. So the macrophages have to, change uniforms.
Perfect way to put it. They undergo what's termed an alternative activation into the M2 phenotype. They physically alter their internal chemistry to become anti-inflammatory.
Oh, wow.
Yeah, they start producing arginase, they pacify the surrounding cells, they swallow up the cellular debris, and they actively promote the rebuilding of tissue.
But the body doesn't just do this at the local level of a single twisted ankle, right? When a trauma is massive, this shift happens to the entire body.
Yes. And this is arguably the most dangerous phase of trauma recovery.
Really?
Because when the body experiences a massive systemic injury, it mounts an incredibly aggressive immune response known as a Th1 or infection-fighting response.
Okay.
But if that Th1 response rages for too long, it will destroy the host. So to save itself from its own fire, the body eventually forces a massive systemic shift into a Th2 response.
And a Th2 response is heavily immunosuppressive.
It's severely immunosuppressive. It's like trying to put out a forest fire by flooding the entire valley.
Oh, man.
Yeah, the fire goes out, but now everything is underwater. The body violently shuts down the production of pro-inflammatory cytokines across the board.
So they have no defenses left.
Exactly. This mechanism explains why severe trauma patients will miraculously survive the initial devastating injury, only to suddenly succumb to a minor respiratory infection a week later in the ICU.
Because their immune system essentially exhausted itself, pulled the emergency brake way too hard, and left the fortress completely unguarded.
It's an incredible biological tightrope walk.
It really is. But, all of this cellular warfare ignores a massive logistical hurdle.
Which is?
How do these millions of neutrophils and macrophages actually travel to the injury? They have to use the body's highway system, the blood vessels.
Right, they have to commute.
Yeah. But the vascular endothelium, the slick inner lining of those vessels, isn't just a passive pipe. The sources say it's an active, heavily armed checkpoint.
Oh, the vascular endothelium is the ultimate gatekeeper. It dictates exactly which immune cells are allowed to pull over, exit the bloodstream, and enter an injured tissue.
And the physical mechanics of how a cell pulls over, a process biologists call leukocyte rolling, is phenomenal.
It's so cool.
Like, picture a white blood cell zooming through your veins at 150 microns per second. In the microscopic world, that is blazing fast. The blood is rushing. But when the vessel wall receives the trauma alarm, the endothelial cells suddenly deploy these sticky protein hooks called selectins onto their surface.
Which function exactly like a strip of molecular Velcro.
Yes. The white blood cell has corresponding receptors. And as it flies by in the rushing blood, it starts catching on these microscopic Velcro hooks.
Just snagging on them.
Exactly. It slows from 150 microns per second, tumbling down to 50, then to a grueling crawl of just 10 microns per second. It literally rolls along the vessel wall, fighting the current, until it comes to a firm stop. Then it flattens out and physically squeezes itself between the cells of the vessel wall and disappears right into the tissue.
It's a stunning mechanical feat, truly. But managing that vascular highway system, keeping those vessels dilated enough for traffic to flow but tight enough to maintain blood pressure, requires a deeply complex molecule.
Nitric oxide, right? And
Oh, nitric oxide, exactly.
But how does a simple gas manage an entire vascular network?
Think of nitric oxide like the pressurized fluid in a massive hydraulic system. Under normal, healthy conditions, your endothelial cells produce a steady, low hum of NO.
Just a baseline.
Right, a baseline. This maintains the perfect hydraulic tension. It keeps the smooth muscles around the blood vessels relaxed and prevents sticky platelets from randomly clumping together.
But a massive physical trauma blows that hydraulic system wide open.
Wide open.
The sources detail how severe injury causes a huge spike in a specific enzyme called ionase-inducible nitric oxide synthase. The body suddenly floods the entire vascular system with massive amounts of nitric oxide.
Which is a huge problem.
Yeah, the vessels dilate uncontrollably, the hydraulic pressure plummets, and the patient enters a dangerous state of circulatory shock.
And naturally, when doctors first observe this massive NO flood in patients suffering from severe sepsis and shock, they assume the solution was simple.
Turn off the tap.
Turn off the tap.
Right. And the text brings up this fascinating medical mystery. Doctors ran a clinical trial where they gave septic patients a drug designed to completely block all nitric oxide production.
Which makes logical sense.
Right, the logic makes perfect sense. If too much NO is causing the shock, just block it. But it backfired catastrophically. The total blockade actually increased mortality. Patients died faster.
Yeah, it was a disaster.
Why did blocking the exact chemical causing the shock make the situation worse?
Because nitric oxide is not just a simple vasodilator, it's a critical immunoregulator. It modulates how your T cells function, how your cells consume oxygen, and how cytokines are produced.
Oh, wow.
So when doctors used a non-selective inhibitor, meaning they blocked the dangerous flooding NO, but they also blocked the baseline healthy NO, they completely drained the hydraulic fluid.
They destroyed the body's entire vascular and immune balancing act.
Exactly. They cut the brake lines while trying to fix a leak.
Oh, that's a brutal analogy, but it fits perfectly.
It's exactly the problem. However, the sources note that when researchers adjusted their approach in animal models and used a highly selective inhibitor, one that only shut down the flooding ionos while leaving the baseline NO intact, the animal's organs were protected and survival actually improved.
Wow.
Yeah, in systemic trauma, blunt force medical interventions rarely work. Precision is everything.
Precision that the body is desperately trying to maintain while burning through like an astronomical amount of
Energy demands are insane.
Which brings us to the final critical piece of this puzzle. The supply lines. Fighting a microscopic world war, reprogramming DNA, and shifting immune responses requires a massive, immediate source of fuel.
Yep.
How does the body power all of this if the patient is lying incapacitated in a hospital bed not eating?
Well, the body is forced to instantly reprioritize its entire metabolic system. And the biological math behind this shift is utterly ruthless.
Let's look at that math from the sources because it paints a really stark picture.
Let's do it.
A healthy adult needs about 1,800 calories a day just to maintain a resting state. But the real bottleneck isn't just calories, it's pure glucose. Your brain and your red blood cells are what biologists call obligate glycolytic.
Meaning they absolutely demand pure glucose to function. They cannot run on complex fats. They're picky engines that only take premium fuel.
And they demand about 180 grams of that premium glucose every single day. But here is the terrifying reality.
Yeah.
Your liver, which serves as the body's main glucose pantry, only stores about 75 to 100 grams of glycogen.
Right. Which means if you're fasting or if you're unconscious due to a massive injury, your liver's entire glucose supply is completely wiped out in less than 16 hours.
A 16-hour countdown clock before the brain runs out of its preferred fuel.
It's ticking.
Now, I know what you might be thinking listening to this. I have muscles. Muscles store plenty of glycogen.
And they do.
They do. There's a massive reservoir of about 250 grams of glycogen locked inside your skeletal muscle. But the deep dive highlights this incredibly selfish biological quirk. Muscle cells lack a specific enzyme called glucose-6-phosphatase.
Yeah, and without that specific enzyme, the muscle cell cannot release its stored glucose back into the bloodstream.
So the muscle can use its own glycogen to power a sprint, but it physically cannot share it with the rest of the body.
It's locked in.
So your brain is starving, the liver pantry is empty,
Yeah.
and the immune system is screaming for massive amounts of energy to fight this systemic trauma war. Where does the fuel come from?
The body has no choice but to initiate a scorched earth policy. To keep the brain online and to fuel the massive inflammatory response, the body pivots to cannibalizing its own tissues.
It starts tearing down the walls of its own house just to keep the furnace burning.
Literally. It begins aggressively breaking down its own skeletal muscle protein, converting those amino acids into usable glucose through a process called gluconeogenesis.
So it's melting down the muscle.
Yeah, and concurrently, it taps heavily into its fat stores. A fasting, traumatized adult will burn through about 160 grams of fat a day, frantically converting it into fatty acids and ketones to spare whatever precious little glucose remains for the brain and the immune infantry.
It's a profound, desperate act of biological survival, and it really brings this entire journey full circle.
It really does.
We started this deep dive talking about the murkiness of physical trauma, about this hidden war room inside you, and look at the staggering ground we've covered today.
The sheer complexity of it is humbling, honestly.
We've gone from gut-synthesized serotonin acting as a chemical beacon to the genetic vault being hacked by stat couriers.
Yep.
We've watched neutrophils throw Spider-Man webs of their own DNA, seen white blood cells catch onto vascular Velcro, and counted down the 16-hour ticking clock of our liver's energy stores as the body literally cannibalizes itself to keep your brain alive.
It's a potent reminder of the miraculous, silent choreography happening inside you at this very moment. But, you know, as we unpack this millions of years old machinery, it leaves us with a deeply provocative thought.
I like where this is going. What's the takeaway?
Well, consider the evolutionary purpose of this system. This immensely powerful, scorched earth biological response evolved to save us from one specific reality. Massive, catastrophic physical trauma.
Like bear attacks.
Bear attacks, falling off cliffs, uncontrolled, life-threatening bleeding.
The brutal physical realities of the ancient world.
Right. But look at the modern world you and I live in. The traumas we face on a daily basis are rarely physical.
That's true.
They're chronic psychological stress, they're relentless sleep deprivation, they're toxic work environments and financial anxieties. These are modern, sterile stresses. So the lingering question is, how does this ancient, aggressive, inflammatory machinery respond to our modern reality?
Oh, wow.
Does our own internal war room, armed with epigenetic shifts, tissue-destroying macrophages, and vascular alarms, does it sometimes get tricked into fighting a war that isn't really there?
That is fascinating.
Are we suffering from chronic, low-grade systemic inflammation simply because our primal programming doesn't know the difference between a saber-toothed tiger and a panic attack before a morning meeting?
That is a chilling thought to end on, because it implies that massive systemic trauma response isn't just reserved for patients in an intensive care unit. It might be happening at a low boil inside all of us right now.
Exactly.
Well, the next time you get a simple paper cut, or even just feel your heart race when your phone rings, I hope you think differently about the microscopic world war mobilizing inside your veins. Thank you for joining us on this deep dive. We'll see you next time.